So when you want to solve a physics problem, you always have to choose your frame of reference. And you usually choose your frame of reference to make it easy to solve. So for example, if I'm going to drop a ball, for example, here on planet Earth, I don't choose a reference frame of the Earth rotating and the Earth going around the sun. I choose just right here in this room. So if I drop this ball, it goes straight to the ground. So if we look at this from a mathematical point of view, we want to choose a reference frame which is really fixed to the place that you're interested in. So let's try that.
Yep, so let's imagine we've got two barges. There's a front barge, that's you on it. I've painted you in green.
Oh, that's me, good.
And I'm over here, I'm the invisible man on this one. And this would be the coordinates you're using. You've got X, Y, and Z coordinates and also a clock to measure time, and I'm measuring it with respect to this. So if I'm doing my experiment here, I would use these coordinates naturally, and you'd use those. The question is, how do we convert between these things? So if you're just doing your own experiment, Galilean relativity tells you everything should work fine in your coordinate system. If I'm doing things on my barge, everything should work fine for me. But what happens if I'm looking at you as you drift past? How would I measure what you're doing? Well, that always seem to make sense. This could be a place where we can solve this mystery, because if there's some funny thing going on with the conversion, maybe that can help us get out of this whole problem.
Right, so this conversion of what you see in your frame of reference compared to what I see in my frame of reference is called a transform. It's a complicated name for something that's pretty simple. It's just how we convert from your point of view to my point of view.
Yep. So what we're going to do now is go through what you would expect to be a common sense transform. This is probably something that any physics student has used a million times without even thinking about it, without giving it a name, converting from one set of coordinates to another. So we're going to do what you'd expect from common sense, and then we're going to start mucking it up and playing with it and see if we can come up with some relativity. But first of all, let's just leave our common sense on. We'll turn it off a bit later.
Yep. And
see what we'd expect the common sense transform to be. So the key thing here is going to be the concept of an event. You've got a wave there. That was you waving. And an event in relativity is something that is located both in space and in time. Right. So there was a particular time and a particular position where you waved.
Right, and so there was a position, so let's look at that, of the event. And so at some point, I'm going to have a coordinate, the clock will have a time, and we want to see how my version of coordinates and time compared to yours.
Yep.
And that's the notion of the transform.
Yes, so you're measuring it with respect to your x, y, z, and t, and I'm measuring with respect to my x prime, y prime, z prime, and t prime.
Right.
So let's look at how we do it. So there's the actual moment, a freeze frame from the image where you've waved your hand up. So the place is here. So there's your x coordinate,
yep.
Y coordinate 0, and there's a z coordinate, and you've got a time t as measured by your clock.
Right.
And the question is, if I'm trying to measure that same event, I'm looking at you as you go past, what would I measure as the x,
right.
y, z, and t coordinates with respect to my coordinates, which are fixed in my barge?
Right. So our barges are on the same piece of water.
Yep.
So we're going to have these new coordinates, which we're going to call x prime, y prime, z prime, and t prime, which are your versions of my event.
So measuring with respect to my rulers, when did you raise your hand?
Right.
Well, the easy one is the z, the height. So
right, because we're on the same body of water in this case, so
yep.
we have the same reference frame.
So we're measuring z and z prime off the same basis, so the height
there's
of your
my
hand will be exactly the same.
Right.
Now the y coordinate will be a bit different because you're to the side, so that'll just be a constant offset, which will be however far apart we are. So let's say you're a metre to the side over there, then whatever y coordinate your hand is, mine will be that plus a metre, plus whatever the separation is. So that's also pretty easy.
Yep.
Time would also be easier, and presumably our clocks are not going to change. Ha ha, who'd come up with an idea like that?
Your watch and my watch will have the same thing.
Yep. Okay. So the time that you measure in t prime should be the same. So the transform there is very easy. It's the same time, same z. The y is just offset by a constant. The tricky bit is going to be the x, because
I'm moving.
You're moving relative to me, and we're both moving in this case. But what matters is the relative speed. So as you go that way, if you raised your hand now, as opposed to raised it a bit later, if you did it a bit later, you'd be further over. So what x prime I measure is going to depend not only on what x you had, but also on what time you raised it. If you raised it later, because of course for you, you're raising it at the same place. Same x every time. But for me, it's going to change.
And it depends on my velocity.
Relative to me.
Yes.
So if we have the velocity relative to me, because I'm moving this way and you're moving that way, so we take your velocity and subtract mine, so we get the relative speed, and call that v, then my coordinate, you will have moved distance v times t. And it's your x, so the x prime I measure will be your x plus that v times t. So the longer you wait before raising your hand, the bigger mine will be.
Okay, so that seems straightforward enough.
Okay, so this is a common sense, actually wrong, transform. So we get x prime is just what I measure for x, for your hand raising event is just what you measure plus v times t. Z's are the same, y is just offset by a constant, I haven't bothered showing that, and the time is the same. So that's common sense, but remember we've got this paradox. We've got light travelling at the same speed and violating Galileo's relativity, and what the hell's going on here? Perhaps we could muck up with these, perhaps we could play with these.
Sounds like a good idea to me. I can't think of anything else to do.
Yeah, we're pretty stuck here.